Well, maybe then they wouldn't be interested because they find me dull. I find me dull sometimes. Okay, let's take a look. So, as we said yesterday, a reaction progressing increases the rate of its reverse reaction and vice versa. All right, so for some reaction, if we start with just the reactant, we'd expect to see this trend in reaction rates. All right, let's take a look. So we're going to go with a very simple reaction here, just like yesterday. We start with some A, and it gives us B. Right? And what we'd expect is that if we take a look at the concentration of A over time.
Excuse the interruption.
Yep. Hello?
Hi, Mr. Orlando.
Yeah.
There's a gentleman from Long and McQuaid here.
Oh, great. Okay. Yeah, I'll be down in just a minute.
Thank you.
Yeah, the problem is I have to give him something. Could you go get him and have him come here? Yeah. Great. Okay. Yeah. Cool. Okay, so we start with A, and we said yesterday that it's going to go down. It's going to get used up. But then at a certain point, we expect to see this kind of thing, right? Where eventually it reaches a steady state, all right? Not much of a graph, but there we are. And then we have this one, and maybe this crosses, maybe it doesn't. I'm going to have it not cross. Whatever, we're going to see, we expect to see some steady state like that as well. They kind of trade off each other, all right? They're related to each other. And at this point, all through this segment, we would say that if this is reaction 1 and this is reaction 2, we would say, well, actually, we can even break it down to here. Right here, we can say that the rate of the first reaction is greater than the rate of the second. Right? Does that make sense? And that's true here because A is getting used up, and it's true here, and it's true here, and it's true here. But then for a little bit, in fact, maybe I'll just trace it like that. But then for a little bit, what's true? Well, for a little bit, it's true that the rate of the reverse reaction is faster, right? Okay. And you can look at that from either graph, right? If we want to just use the yellow highlighter for this, we could say as long as A is going down, well, then the first reaction must be happening faster. As long as B is going up, the first reaction must be going faster. But then, if it's this way, then when it switches, that must mean the second reaction is going faster, and so on and so forth, right? These just go back and forth. I should really have not done that, because that's wrong. Right? So anytime that we have that, and you can see it from the graph, right? But then we reach this other point where the two rates are equal. Oh, I screwed all that up. Okay, you know, I'm not using the highlighter because I already did it with the colors. So really, what am I trying to prove here? I'm just being difficult. That's what I'm being. Let never be said that I'm difficult. But then what is true here? From here on in, we can say that rate 1 and rate 2 are essentially equal. They may vary a little bit. We may get little wobbles. But for all intents and purposes, they're happening at the same rate. Okay, cool. So we said then that we can make equations from this. I meant to do that up 2 hours ago. Let's make some equations from this. The equilibrium equation, let's start with an easy reaction. A plus B yields C plus D. Yeah. I want you to write a rate law for the forward reaction, and I want you to write a rate law for the reverse reaction. All right, that's what we ended with last unit. So you should be able to tell me that. Get on it. Hi, how you doing? I'm doing well, thanks. The curly's sitting on my rack. Do you be cool if I just took these now and then brought the one that isn't working for one break time when I head home? Yeah. Can we make that work? Yeah. Is that okay? Yeah, that's cool. Thanks. So just awesome. Just trying to. Thank you so much for doing this. Yeah, you're in this dog's breakfast. 3 minutes. You 4 from the board and like 100% of the radio frequency. So I was thinking interference, but then I like literally took it to a different place in the building, power won't connect, and then it's also doing like compact line. So I don't know what's up with that.
Yeah.
It's another bus.
Yep.
Totally different because you got cell. We have one sure kit.
Yep.
Where the only thing we don't have for it is a power headset. Receiver, we got the speakers in the back. Yeah. That's
Yeah. So.
because it's that proprietary sure like 4-pin.
Yeah. So we got Apex cells.
Oh, do that?
We sell a Fender 10 like that. A lot of people like to go on back too, but it comes with all the possible protections.
Oh,
so for sure, it's not whatever.
Cool. That's why
I'm just gonna take the photo of the serial number so I can put it on.
Thank you. And like I said, I will get it.
Yeah, bring it on back to the I think that
I should be there in plenty of time. If not, can I just click
yeah, just
to
leave
you?
it with them and I'll deal with it tomorrow. Yeah, awesome.
Thank you so much. I really appreciate it. All right. What are my 2 rate laws? What are my 2 rate laws? What would if we call this reaction 1? We call this reaction 2. My 2 rate laws. What would the rate of the first reaction be? What does it depend on? First of all, it's going to be some constant K, which will be constant so long as we are a standard constant temperature and pressure. I'm going to call it K1 because we're talking about reaction 1, okay? And then what's here? Concentration of A and the concentration of B, okay? Now, we have said that up till now, you have to determine these experimentally. And again, when you're dealing with the rate of a reaction in the wild where you're not thinking about its reverse, that's true. But as things approach equilibrium, all the reaction rates start to get the same, right? So remember we said the reason you have to get these experimentally is because it may happen in multiple steps, and those individual steps, one of them may be the slowest. So it may be that even though we need 5 hydrogens to bump into each other, it's really only one collision of a hydrogen into a B, whatever, like all that sort of thing, right? But as you approach equilibrium, every reaction involved is getting to a steady state. Does that make sense? At equilibrium, there's no longer slow reactions and fast reactions. All the reactions are happening at the same rate. Does that make sense? Which means that even if in the wild, these exponents are different from the coefficients here, when you get near equilibrium, the rates will depend on how many are in the reaction. If you want me to walk you through that mathematically one-on-one, I'm not going to do it for everyone. I can show you how in a 6-step reaction with one slow reaction, the one that determines the rate under like extreme conditions when it's happening quickly is the slowest reaction, but that when the rates get close to each other and you put all the rate laws of those 6 steps together, they will always cancel out so that the concentrations you're left with will be these exponents from the thing. Even if one of the slow steps needed 6 of these to bump into each other, if you only need one A for every C and D you make, and one B for every C and D you make, those will cancel such that by the time you're done, because the coefficients here are 1 and 1, these both end up as being first order at equilibrium. If you want to just trust me on that, trust me. If you want me to show you the math, I'm happy to. If enough people say they want me to show you the math, I could even make like a little reach ahead lesson for it. I don't want to do it with all of you because it's frankly a bit of a math rabbit hole, and I found that some people find it more confusing than not. So just trust me that when we're talking at equilibrium, you just grab the coefficients from the reaction. In this case, both those coefficients are 1. What will the rate of reaction 2 be? What will the rate of reaction 2 be? K2 times concentration of C times concentration of D. Okay. Does that make sense? Feel comfortable with that? Okay. Now, these are the rate laws for reactions 1 and 2. At equilibrium, what will be true? So, however much A, however much B we start with, however much C, however much D we start with, at some point, what's going to happen to these? Because those are reactions that go in the opposite direction. They're going to what? They're going to be equal to each other. The two rates will equal each other. At equilibrium, rate 1 will be equal to rate 2. Which means we can make a new statement, which is what? Because two things equal to the same thing are equal to each other. At equilibrium, we can say what is true. Combine these into a single equation for me. Yeah.
K1, the concentration of A and the concentration of B equals K2, concentration of C and concentration of B.
Okay. That is true. Now, if I wanted to, I could rearrange this. I could leave it like that. That's a true statement. And there's times when that's a useful arrangement. But the nice thing is this. What is no longer in this equation? Interestingly. What does this equation actually not care about, even though we had to use it to get here? Rate. So this equation now no longer, it doesn't tell us how fast the reaction is happening. And we don't really care how fast the reaction is happening because at equilibrium, that's the least important information because whatever the rate is of one, the rate of the other one's the opposite and they're undoing each other. So who cares, right? Rather, this no longer includes rate. But what it does tell us is that some constant times the concentrations of the reactants will be equal to some other constant times the concentration of the products. At equilibrium, we can make a statement about the concentrations. And when you want to compare two things, because here we have kind of what we call our reactants, and here we have the concentration of our products, right? Why wouldn't I put that around reactants, since that's what concentration means? My square brackets, with each passing year, become more just the exact same as my round brackets. I don't know why. Yeah. Which one? It's a K. I'm sorry, my Ks are terrible. People make fun of my Ks all the time, and it makes me sad. But the problem is I'm trying to show you it's a lowercase k, because uppercase K is different. And we're going to be using it in about 4 seconds.
Oh.
So these are lowercase Ks. Do you want me to mention that? We use lowercase k for rate constants.
Is it lowercase the same as uppercase? Just a little bigger.
That's like regular, but if you're like a cursive writing, the uppercase K is like boom, 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 and then the lowercase one has like a little loopy loop.
Yes. That's a K versus K. Anyway. Okay.
Do you see what I'm saying?
Yeah. Boom, boom, boom versus loopy loop. Got it. Okay, let's move on. It's also how they describe my fighting style. Boom, 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 loopy loop. Anyway, let's get going. Yeah, you know, he knows. So, what can we do with this? Well, we can do with this, quiet. We can do this, something incredibly useful. We can make a ratio. A ratio. Chemistry, as you know, is all about ratios. We love to multiply and divide. Well, what we can say here is let's turn this into, first of all, do we want to have two constant values in an equation? Is that ever a good idea? No. Why have two constants when you can have one constant? Is there any reason we can't combine K1 and K2? No. Now, how would we have to do that? We'd have to move one or the other. Okay, which one do we want to move? Okay, we'll move K2. I like that. So right now, what do I have to do to move it? Can I just subtract it? I'd have to divide, right? So we could say K1 times A times B divided by K2. But while I'm at it, why don't I put all my concentrations as a ratio? Because the real power of this is it's going to say that there's a ratio relationship to things. Does that make sense? So let's move a K to the other side. So our constants are both here, K1 over K2. And since we have two constants together, well, let's just call it a new constant. Ready? K. And when is this only true? It's only true at equilibrium. So our generic version of this will be KEQ. Though you'll see KSP if we're talking about solubility, Ka for acids, Kb for base. The real giveaway is if it's an uppercase K, it's an equilibrium constant. Which we're going to write on the next page. So you don't have to write here. We're going to write that on the next page. Now, to get the two Ks by itself, what did I have to move from this side? So I had to move this K over here, but then I wanted these just to be by themselves. I had to move the A and the B. Can I just subtract them? I have to divide them. So on this side now, we'd have the concentration of C times the concentration of D divided by concentration of A times concentration of B. This is actually going to start the next page, but it's kind of nice to have worked it out here. And then we'll use a more generic example here. So look, why is this a useful statement? This is actually incredibly powerful. If you let a reaction sit and happen until it settles down, if you measure the concentration of the products and you measure the concentration of the reactants, these two multiplied by together, divided by these two multiplied by together, will always equal this value for this reaction under that temperature and pressure, no matter what concentrations you start with. That makes sense? As long as you know the temperature and pressure, this value never changes. So you can throw any concentrations you want into a bottle. They're going to go where they go. They're going to move all around. You'll get all kinds of different outcomes based on what you put in, but it will always satisfy this equation. When it's settled down to an equilibrium, you multiply the products concentrations together and divide it by the concentrations of the reactants, it's going to be that same value, which means we can make predictions. Does that make sense? We can make predictions. We can say, if I start and we're going to get into that. That's what we're going to do this unit. But does that make sense? This gives us the power of prediction over reactions that are at equilibrium. And again, what's the definition of a reaction at equilibrium? It's some reaction that can go forward, can happen, but can also go in, for you guys would be this way, right? It can go forward, but it can also go backwards. And at some point, a reaction that can do both will get to a point where both are happening at the same rapidity. And we say that's at equilibrium. And it means that even though both reactions are happening, the concentrations are going to be constant. And when the concentrations reach that steady state, they'll satisfy this equation. Okay, so there is one thing, which is we haven't worked with coefficients. So let's work with coefficients. Let's take our same reaction. A plus B gives us C plus D. By the way, there's nothing magical about having two products and two reactants. It's just easy to work with. And let's give them coefficients. And ready, I'm going to get very high tech. Let's call the coefficient on A. Let's call the coefficient on B. And let's call the coefficient on C. And let's call the coefficient on D. No. So here, we can jump right ahead. We don't have to start with rates. All right, we could say the rate of the forward reaction is going to depend on the concentration of A and the concentration of B. And we're going to say, even if under normal conditions, one might be first order, one might be third order, if we let it sit long enough, we know that the slowest reaction and the fastest reaction will all meet up in the middle, and everything's going to cancel out so that this many A's have to bump into each other. So it will be, if A is 3, this will be order 3. If A is 1, this will be order 1. If A is 2, this will be order 2. Likewise with B. Even though maybe when you do it, it's 0 order for B under normal conditions, like early on when you start, because those rate laws we did, they're really about how the reaction starts, right? This is now about when the reaction is stopping, right, where it's steadying down. And by the time it steadies down, the slow reactions and the fast reactions all happen the same, and this coefficient will be the power on this. So we could write a rate law for the forward reaction, say it's K times the concentration of A to the exponent little a, times concentration of B to the exponent little b. That's the forward reaction. And the reverse reaction will depend on some constant K times the concentration of C to the exponent little. But we've shown that math all works out to give us this. Does that make sense? So this is what we're going to call mass action laws, or just equilibrium laws, where we can say the K value of this reaction, and this EQ, if you wanted to put the K of A plus B yields C plus D, that'd be fine. I'm never going to do that because that's a lot of writing. Usually we'll just say the equilibrium constant, KQ, is equal to a ratio. And the ratio we're going to get is that on the top, we're talking about the reverse reaction, actually. We're talking about what drives this reaction backwards. And that would be C. And what exponent is it going to be put to? Yeah, whatever that is. And then we're going to have the concentration of D. And what exponent is it going to be put to? Right? And on the bottom, we're going to have what? A to the concentration of whatever its coefficient is. And it's going to be multiplied by, and obviously you know this, but let's just say it, to the exponent of B. Okay. That is our equilibrium expression. Okay? How's that feel? Not too bad? Okay? Pretty all right? That's the law. That's the law. And again, I want you to remember this. This might even be worth putting a note here. Now that we're using the coefficients for equilibrium, don't start using them for rates. All right? Because again, rates aren't using those rate laws we've written, they're not focused on down at equilibrium. Equilibrium's when things get slow and boring. The rate equations you used last unit are about how fast reactions are going to start off at and be at early on. So, in other words, they're not dealing with equilibrium states. So now, let's just say this. Use coefficients for equilibrium laws KEQ equals, but not for rate laws. That's important because, again, rate laws, you can't assume that early on all the reactions are happening at the same speed. In fact, we know they don't. There will be a slow part of the reaction. That will be what determines the rate. But at equilibrium, every part's the slow part. So now you include them all. So you can only use the coefficients for rate laws at equilibrium. So that means we can use them for equilibrium laws, but we can't use them for rate laws unless you've done the hard work of figuring out every single step that happens in a reaction and actually including all, if it's an eight-step reaction where 8 things have to happen in a row, if you wrote all 8 rate laws, you would find that they cancel out to the coefficients. That's a lot of math. All right? We're not going to do that. So just keep in mind, what people always do is then all of a sudden you give them a question from last unit and they just grab this number and say, oh, it's second order. That works for equilibrium. It's not true when a reaction starts. So true for equilibrium laws, not true for rate laws. Does that pass? This is a lot of stuff. Did that make sense? Would you tell me if it didn't? Yeah. So how many A's are involved in this reaction? That, when we get down to equilibrium, because all the different reaction, again, we show this as one reaction, but what might actually happen here, this could actually be a bunch of reactions. This could actually start with an A bumping into another A and making something X. Then that X might bump into a B, and it might give us a thing Y and give us back the original A. Then that Y might bump into another B and make a thing Z. Then that Z might decompose into getting our B back and now give us C and D, which are the 2 things we started. So it could actually be 1, 2, 3, 4 reactions. Does that make sense? And if you wanted to work out rate laws and use the exponents, you would have to know this. And you'd have to know that actually this one depends on the concentration of A squared. This one depends on the concentration of X squared, of X and the concentration of B. But that concentration of X, we don't calculate. This one depends on the concentration of Y and the concentration of B. And this one just depends on the concentration of Z, right? And obviously a constant in each case. And it could be the case that this is the slow reaction. So at a normal concentration early on, the equilibrium expression for this might be that rate is equal to K times the concentration of A squared, which would mean that even though this has an A and a B in it, the rate law for this might be second order for A when we're starting the reaction off, the stuff we looked at last unit, right? And how would you figure that out? Well, you'd do concentration of A, concentration of B, and the initial rate, right? And you'd try it at 0.1 and say this is 8. And then you'd try it at 0.2 and 0.1, and you'd find that the rate goes, well, we doubled this, right? But we set second order, so if it's second order, this would get multiplied by 4. So this would have to be 32. And if we put this back to 0.1, and now we double B, we see that this actually doesn't change at all. And so we'd say, therefore, rate equals K times the concentration of A squared. But that's not talking about the rate at equilibrium. That's actually all of last unit. Everything we did is based on what we call the initial rate, how fast the reaction is at the start. Does that make sense? Now we're doing something totally different. Now we're talking about not how fast is the reaction at the start. Now we're talking about how fast is the reaction when it stops. And by stops, we mean equals out. And by the time it stops, all the reactions are at equal speeds, which means now you can just use these values as the coefficient. It's actually much easier because you don't have to worry about which step's fastest, which step's slowest. They're all slow. They're all going the same speed. That's why they're at equilibrium. So this is the general form. And it's easy. This is much easier than last unit. Last unit, you had to look at a bunch of charts and say, oh, this doubles, what happens to that, all that crap. Here, look at the chemical equation, throw the numbers in. Equilibrium is friendly. It's where everything's going the same speed. Makes the math easier. So this unit's easier math than last unit. At first. No, even at the end. If you want to look up your math notes and look up quadratic equation and do like a couple practice worksheets, you'll be, we're about 4 days away from doing some quadratics. So you can give yourself a head start. That's 2D, pardon me. If you want to look up your 2D math, practice your quadratic equation, x equals negative b plus or minus the square root of b squared minus 4ac. Why couldn't Kelford come in now? All over 2a. You might want to remind yourself of that because we're going to be using that. That's as tricky as the math gets. I won't even make you factor. We'll just go right to the quadratic equation. All right, so let's practice this. Here's a real reaction, and I want to note something. The way we write a reaction at equilibrium, I didn't mention this yesterday, is we want to show that the reaction goes both forwards and backwards. So instead of writing two reactions, which is annoying, we draw what we call an equilibrium arrow, which tells us that this reaction goes in both directions. So a reaction that goes all the way, we wouldn't draw this arrow. We just draw the arrow like we always have. But a reaction that settles into an equilibrium, we draw with this arrow here, yeah.
And now it actually is to look like an equal sign.
It does kind of look like an equal sign, doesn't it? So now, I kind of hate that symbol they used. Not that mine looks much better, but hey, there it is. So now I want you to write a KEQ statement for this reaction. For this reaction, at some given temperature, what is KEQ? All right? You're obviously not going to be able to solve for the number. I just want the law. I want the equation, but not put a value. So, remember, we said what goes on the top, reactants or products? Products. That's arbitrary, by the way. Nothing magical about that. But we line these things up. You'll see, like, for example, when we did calculating delta H from formation enthalpies, we do products minus reactants. Here we do, when calculating KEQ, products divided by reactants. That's a bit of a standard in chemistry. We tend to do products then reactants when we do our equations. Just kind of a thing we do. Oh boy. So try that out, see what we get. Should be straightforward, and I apologize for the numbers not being subscript. I used to use a font, anyway, don't worry about it. Point being, I done screwed up and I apologize. All right, what do we get? Talk to me. It's a ratio. We said the products go on the top, and we said the reactants are going to go on the bottom. So what's up here? Concentration of CO2. And does it need an exponent? Yeah, what exponent? Good. And the concentration of? Great. And does it need an exponent? What is it? Awesome. What about the bottom? Yeah, what is that? Give it a name. You can do organic chemistry. What's the exponent, by the way? Okay, so we have a C stuck to another C, and then they're both stuck to a hydrogen. Obviously, that doesn't work. What has to happen to make it work? Triple. Yeah, right? We could count electrons. One for the hydrogen, cool. One for the hydrogen. Two for, yeah. And then 1, 2, 3, 4. It would be F. F what? Come on now. Ethine, good. What's the hybridization state of this carbon? SP what? Well, I guess we can't tell that yet. Let's ask this. How many pi bonds is it making? How many pi bonds? 2. How many sigma bonds? Really? 2. How many lone pairs? None. Okay, what do pi bonds go in? P orbitals. What do sigma bonds and lone pairs go in? sp hybrids, right? And in this case, how many do we need? We need to keep 2 p orbitals, which means we need how many hybrids? 2 hybrids. So how many an s and how many p's make 2 hybrids? Just 1, right? So we'd get a 1s, would be full for the carbon, and then we'd get 2sp, and an s and 1 p orbital will give us 2 of them, and we'd also have 2p, and how many of those would we have? 2. And since the bonds, how many electrons here? Like that? Do they go in like that? First of all, that would be a what? A lone pair. But do we see a lone pair on that carbon? No. And also there'd be nothing in this hybrid orbital, which doesn't happen. So those will both be our sigma bonds, and those will be our pi bonds. Hey, does carbon have 4 electrons to work with? Oh yeah, good. You got it. What's the bond angle? 180 degrees. Good. What would we describe its shape as? Oh, you guys are good. All right.
Did you train them just to do that while I was standing here?
No, they're good, right?
Yeah.
Pretty good.
After you know you're doing beer pong at lunch? Okay. The ping pong balls are...
I understand this is student council related, but that was like the most frat moment I've ever heard in my life. Hey, Orlando, I need to...
Because he didn't know.
I need to interrupt your chemistry lesson. Dude, you didn't forget about beer pong, right? Definitely feel like I'm back in university. Thank you. What's the last thing here? After our ethyne. Yeah, and how much of that do we need? So what goes up here? Awesome. That will be true at equilibrium. All right, that's it. Which means, and this is true as long as what is, because this is based on the 2 rate laws, and they are true as long as temperature and pressure remain constant. Now you'll see that when we work with gases, that's going to be problematic because, this has 4, 5, 6 moles of gas, where over here we had 7 moles of gas, so that's going to change your pressure. So that gets messy, but say you have a really clever system that changes the volume as the reaction happens to keep the pressure constant. Okay, let's try another reaction. PCl5 can undergo decomposition to form PCl3 and Cl2, but that reaction can also undo itself. And at equilibrium, as soon as you see equilibrium, as soon as you see that, just stop what you're doing and write a KEQ statement. Anytime you see equilibrium, be like, okay, I'm at equilibrium. Let's write an equilibrium statement. What's the equilibrium statement for this reaction? Yep.
Do we take their concentration equivalent?
Yep.
Okay, so it would be 0.25.
You're totally right, but can we start with the general form?
Oh.
You're 100% right.
PCl3.
Yep.
And then
Exponent?
0. Nothing.
0 or
1.
1, yeah. But you're right, nothing. We don't write it.
CL2.
Yep.
2.1.
Yep.
And then at the bottom we have PCl5 to exponent 1.
Okay, good. So just listen. You are going to be making equilibrium constants for every equilibrium equation you get this whole unit. So just get in that habit. As soon as you see equilibrium and you have an equation should always, and a chemical equation should always be paired with an equilibrium equation because you're going to use both. Does that make sense? So, these are paired, right? This chemical equilibrium gives us this equilibrium expression is something you'll see, equilibrium equation, equilibrium law. They all mean the same thing. Their way of saying, at equilibrium, this will be true. Now, they've given us a question. This 24.2, am I going to have to work with that? Nah. Why does it matter? It matters because if the temperature changed, what would change? KQ. Does that make sense? So this is imagining some imaginary world where this reaction can happen and it causes no temperature change whatsoever. By the way, is that true? No. But we're going to pretend it's true for our math, because if we didn't, we'd have to do calculus. We're not going to do calculus right now. Does that make sense? Life gets a little trickier, and we're not going to in this course. Don't worry. For this whole course, we're going to just assume that things remain constant. And it's a safe-ish assumption at small concentrations. So we know what we're mostly going to work with? Small concentrations, yeah. So now we have an expression, and what does it want us to find? It wants us to find what is KEQ. What do we have to know if we're going to know KEQ? Well, we know our concentrations, right? Does that make sense? So with all that in mind, we write an equilibrium expression, and then we say, okay, what does it depend on? Well, it depends on the concentration of PCl5, but hey, I know that. What else does it depend on? Well, the concentration of PCl3, but I know that. And it depends on the concentration of Cl2, but guess what? I know that too. So what then can we do with this expression? You can solve it. That's right. What is the concentration of PCl3? Yeah. Cool. And what is the concentration of Cl2? 0.25 molar. By the way, never mind. I'll talk about that later. I don't want to throw more things at you. What's the concentration of PCl5? 0.15 molar. Good. And now we can just do some math. And, oh golly, what's a quarter of 0.125? That'd be 0.06125. And then 0.6125 divided by 0.15, oh God, is going to be equivalent to, I can do this. Can I do this? I can do this. It's going to be the equivalent of multiplying that by something. That's what. Multiply by 6 divided by 20. So we can do that, right? 6 times 6 is 36. Divided by 2 is like 18. So this should be on the order of like 0.18, sorry, 1.8? Yeah, 1.8 something. All right, somebody do this with a calculator. I don't have a calculator. What is it? Oh, I done screwed up. Whatever. Okay, what is it? 0. Oh, yeah, I was way off. Okay, whatever. Okay, there we go. Oh, because I switched my multiplying and dividing. Because it wasn't 20 26. It was, anyway, okay, that's fine. And what's our unit going to be? Molar times molar is molar squared divided by molar would just be molar. Now, by the way, if you wanted to get hyper particular, you could actually put units on each of these, and it could be molar PCl5, molar PCl3 times molar Cl2 divided by molar PCl5. And that would actually be more accurate, but people never do. They just act like molar is molar is molar, which really isn't very accurate, but that's okay. That's what we do. We can't cheat. And so now we know KEQ. And now we can write the proper rate law, which is we can say, if we wanted to, we could say 0.41. By the way, how many decimal places do I have to work with here? How many sig figs? Do I? How many sig figs? Yeah, because this is 2 sig figs, right? And this is 2 sig figs. And this is 2 sig figs. So we need to round this to this sig fig, so it should be 0.41 molar.
4.2.
Pretty sure I said 4.1. Pretty sure I have a degree in chemistry, except I screwed up filling out my form, so I have a degree in biology, which isn't even what I studied. Anyway, where was I? Okay. Sorry? I didn't take a minor, but I took we don't talk about my education, all right? It was a disaster. It's a disaster. It's embarrassing. I'm a big embarrassment. Anyway, we'll move on. So now, if we want to, we can use that, right? At any point now, we can say, as long as we are at 24.2 degrees Celsius, and the truth is, it should also tell us the pressure, but whatever. 0.42 molar will always equal the concentration of PCl3 times the concentration of Cl2 divided by the concentration of PCl5, right? And now, with that, if we wanted to, we could solve some questions. Does that make sense? Cool. Now, what does this mean? Why is that useful? Well, it's useful because in and of itself, equilibrium is boring. What's true at equilibrium? At equilibrium, everything stays the same. So if at equilibrium everything stays the same, it's kind of a boring thing to bother calculating, don't you think? But of course, nothing stays the same. Everything changes. We live in a dynamic universe. We live in an entropic universe. Things are moving around. We live in a chaotic universe. Things are moving. Perhaps you've noticed. I feel like I'm a good example of this. But things don't stay the same. So this is true at equilibrium. But now what happens if you've reached equilibrium and you introduce a change? At equilibrium, everything reaches a steady state. You can sit down and you can calculate where all the concentrations would be. We're going to do a bunch of practicing of that over the next bunch of days. But you can say at equilibrium, we have this much of this much of this much of that, find the one missing thing. All right, that's a math question, but it's not very exciting. It doesn't really help us. It's not something we'd actually do in the lab. But here's what we do in the lab all the time. We want to drive a reaction. Here's what becomes really interesting. The fact that reactions go forwards and backwards is a real problem for us. We make fertilizers, right, that you spread on, anyone comes from a farm, you spread them on a field and they let things grow. And we use some natural fertilizers, manure, right? But that can't keep pace with our crop production. And before the introduction of artificial fertilizers, the world was in crisis. We had actually just about depleted Europe's soil nutrients, and we had this big population, and plants weren't growing like they used to because we were just drawing nutrients out of the soil too quick, and we couldn't produce fertilizer at a fast enough rate. It was the brink of famine. And scientists could say, well, we could make the nitrate fertilizers we need, but the problem is that as you make them, they like to unmake themselves. It's a real problem. And so what we had to figure out was, well, how can we make them make themselves way more than they unmake themselves? Does that make sense? And this comes with the idea of once something's at equilibrium, how do we introduce change so that the equilibrium can shift? Does that make sense? So let's look at it. This introduces us to an idea called Le Chatelier's principle. We're going to finish up with this tomorrow, but I want to start it today. When a system's at equilibrium, any factor that changes the rate of the forward reaction or the reverse reaction will cause a shift. And the system will readjust and it will form a new equilibrium. Yeah. And we use something called Le Chatelier's principle to tell us how a change in the ecosystem will affect the equilibrium. But listen, you don't need to understand fancy science to understand Le Chatelier's principle. You need to have a small child in your life. Hands up if you have a small child in your life. Or a big child who's an idiot. Or both. Okay, hands up if you're an idiot. And I appreciate your honesty. So listen, here's what you have to know. You're a little kid. You're a little kid. You and the little kid are at equilibrium. Which is to say, you're saying, eat your vegetables, and he is saying, I will not eat my vegetables. And that's the equilibrium. And as fast as you're saying, eat them, he is not eating. Right? This is the shift. Does that make sense? How are you going to do his vegetables? Yes, you don't. It's a trick question. You just don't. You give up. You give up. You say, fine, starve. But here's the point. Shh. The idea is this. You can change the equilibrium, right? You can change, you can go, okay, he's not eating his vegetables. I'm going to get more vegetables. See what that does. And what will he do? He will reject even more vegetables, right? You could get real sneaky. You said, well, what if I pick just one? You do this with a little kid, right? You got a spoonful of peas, he won't eat the damn peas. You're like, get one. Surely he'll eat one just to end this fight. You put one pea on the spoon, you bring it forward, and what's he do? Yeah, rejects that. Doesn't matter. Any change you introduce, they are going to unintroduce. Even better, ever put winter clothes on a little kid? Ever done this joyful activity? You put a boot on. Great, we got a boot on. You got to put the next boot on. What happens to the first boot?
It's gone.
It's off. Oh, it's off. So now you go put the first boot back on. What happens to the second boot? It's off. Give up on boots for a while. You go put a hat on. Now you go back to the boot. What happens to the hat? It's off, right? It's just whatever you do, what's the kid do? The opposite. It reacts in reverse. Does that make sense? This is Le Chatelier's principle, and it says this. This equation predicts that any change you introduce into the system is going to cause the system to react in reverse. Does that make sense? If you think about it, look at the math equation. The math tells us that these three things have to exist in a specific orientation. So they reach a place where they work, right? Now what happens if I go make this number bigger, what has to happen for the math to still be true? If this number goes up, what has to happen? Can these just stay where they are and it still equal this? Nah. So what has to happen to this number? It has to go, nope. That's going to make the problem worse, right? Because the problem right now, what's actually happened to this number? If it was 0.42 before, and maybe I make this twice as big, now this number is 0.82. Does that make sense? Right? That number's too big now. So we know that the reaction is going to start to change. Now the thing is,
excuse the interruption, folks. On today's
we could just make this go down by twice as much. But the problem is, can I make this go down twice as much without changing that also? No, of course I can't. So these are going to have to change together. If this goes up, CL2 is going to have to go down, and PCl5 is going to have to go up. Everything shifts, but it shifts in the opposite of what you did. If you put reactants in...
And this is just a reminder that you can bring your permission forms and any money for tickets to the front boy at lunch for prom. And student council is hosting water polo.
Just waiting on McGlynn to be like, the following students go to Eastdale. And then just start. Anderson, comma, Aiden. All the way down to, do we have a Zed? This has got a last name Zed. Zweers. Anyway, okay. So, however you change it, the math tells us it will change it back in reverse. So, this is Le Chatelier's principle. So if we look here and we have some reaction, A plus B is in equilibrium with C plus D. All right? Once equilibrium is met, we know that the ratio of the concentration of C to D divided by the concentration of A times B is constant, right? But now, what would happen if we added A? Let's say we add A into the equation. Now, the denominator is too big. Does that make sense? Yep, you're good. Which means we have to make the denominator smaller. But while we make the denominator smaller, that means to make the denominator smaller, we have to be using up A and B, right? Which means that in the process of making the denominator smaller, we're also going to be making the numerator bigger. Does that make sense? So if we add A, the result is actually that the reaction is going to, so immediately, what would happen is the concentration of A would go up, right? Just in the immediate moment you add it, and B, C, and D would all be the same, right? Does that make sense? These would be the same, and this would go up. But then we're going to have to get a new equilibrium. Does that make sense? Because now the math doesn't work anymore. And in the new equilibrium, what's going to have to happen, since the concentration of A is too big now, the concentration of A has to go down. But the only way the concentration of A can go down is if what else goes down with it? Because they have to react with each other. So as we use up A, what else is going to get used up? B. So the concentration of A and B will go down. What about the concentration of C and D? Up. They're going to go up. Okay. So listen. Here's the weird thing. At equilibrium, if you have a reaction at equilibrium, if you add a reactant, what it will do is actually make the reactants get used up a bit more, and it will drive the reaction away from the reactants toward the products. Does that make sense? What would happen if I added some D to this equation? It's going to drive it towards the reactants. See that? So we can manipulate. So maybe you have some reaction where this stuff's really important, you need it. This is a really expensive ingredient, and you want to use it all up. This is a real cheap ingredient. And if you normally let it, maybe only 20% of this stuff gets reacted, and the rest just stays there, which is really frustrating. Well, if you're a chemist, you can say, no problem. I understand that the reason all of this isn't getting used up is because it's reaching an equilibrium. I don't want to keep pumping in the expensive ingredient, but I have 3 ways I can handle this. I could add more of the cheap ingredient. That'll keep driving it. But what else I could do? What if I took away this? What if one of these, maybe these are aqueous solutions, but this is a gas. Well, what could I do with the gas? I could let it out. And I could constantly be getting rid of D. And if I'm doing that, that's going to constantly drive the reaction forward. Does that make sense? So Le Chatelier's principle lets us look at a reaction and say, how can I make this reaction do what I want? And that's what we're going to spend the next bunch of days talking about. Does that make sense? Cool. Sorry to go on so long. Have a wonderful day. Be kind to one another. Everyone should come to the play tonight. Your peers have worked very hard on it. And, yes. So come to that too, but you should come tonight too because, support people. They work hard. Or tomorrow night. You got options is what I'm saying.
Tonight, guys.
Sorry?
Food tonight?
Yeah, concessions and,
What time do I come? Do I come just third period?
yeah.
What did you guys?
Can somebody give this to Mr. Alastrek? Thank you very much.
What did you guys do yesterday, third period?
I wanted final copies of people's lab proposals, which I'm going to work out today. And then